Okay, so I understand that I'm here, right? 1, 2, 3. So I like this campus and lake. And this is my talk title, Deep Learning Bulk Spacetime from Boundary Quantum Data. So I guess probably mathematics students look very puzzling about this. But the main keyword is there's a deep learning story here and some space-time story and also quantum story. So this is kind of a symbol of my talk. There's a the two-dimensional space, and this is there's another extra dimension, and there's a kind of a black hole horizon here, and there's some dynamics in this three-dimensional space, and there will be a reflection to the two-dimensional space, something like that. So then it can be understood as a deep learning neural network. So I hope at the end of this talk, this story should be more clear, much clearer for you. Okay, so maybe it's not working. So then, oh, okay. Okay, good. There is a keyword, the holographic principle, and also ADS CMT. So everything looks unfamiliar to you. So let me try to explain one by one. So I'm talking about this paper. My story is based on this, the pioneering paper. This is one of the most cited paper in the theoretical physics. So it's 2018 version, but I believe still this is the top cited paper. And this is Maldacena is one of the author. That's the main author. Okay, so the starting point is the gravity. So then I think you know about the Newton, and if you heard about the gravity, then you will think about the apple. And this apple, maybe it's still not working. What should I do? Oh, is it okay? Yeah. Yeah. Right. So it's about the F equals ma. I think you learn about that from the freshman physics. And this is apple tree in the Cambridge University. Of course, this is not the real one here. This is for the tourist. And nowadays, if you say gravity, then you will think about also black hole, about Einstein. This is the image of the black hole. And Einstein's theory predicted there should be some strange object in the sky, which is called black hole, right? And this is another image of the black hole in our galaxy. This is not in our galaxy. This is in our galaxy. And there was a Nobel Prize for the black hole in 2020. And here, two observational astronomer and the theoretical physicist, Penrose. And you know this famous physicist, Stephen Hawking. And Penrose and Stephen Hawking collaborated in many papers. They were close to each other. However, he got the Nobel Prize, but he didn't. It's not because he is not good, but because he studied something strange. Here I said it's a classical black hole. Classical black hole is Einstein's black hole. Then the original definition is everything goes in to some place, some space-time region, and nothing goes out. A very strange object. And the quantum black hole is a little bit different. So the Stephen Hawking is mostly studied about the quantum black hole. And I like this picture. Actually, the Stephen Hawking was sick in most of his days, but when he was young, he was good. So I think it's probably freshman or junior or sophomore. He was really healthy, but maybe from the graduate students, he got ill. Okay, so this is about the Hawking's black hole. It's a black hole. Whole point is this: black hole is not black; it's a little bit warm, in a way. So black hole has a temperature. This is the Hawking's the formula for temperature. There's T and pi. Mathematicians like this pi, right? And also there are three physics constants: the h-bar Planck's constant, speed of light, and Boltzmann constant. Maybe you don't remember, but this is very important physics constants. And there is a 1 over gm. G is Newton's constant. M is just the only parameter in this simple theory. And this represents the mass of the black hole. And we know these three parameters, and also we know G, and this M is only the free parameter. But if we assume black hole mass is similar to solar mass, then this T is this, 10 to the minus 8 Kelvin. So this is way, way, way below than the universe temperature, background temperature. So it's very hard to observe. So that's one another reason why Hawking was not able to get a Nobel Prize. It's not observable in this setting. But anyway, whole point is the black hole has a temperature. What do you mean by black hole has a temperature? If you just put the thermometer, then you can measure the temperature. No, so you can observe the radiation from the black hole. And then by comparing the black body radiation, so you can say the black hole temperature. The whole point is, if you look at the sky, there's many stars, and also there are black holes. So your mental picture of the black hole, maybe everything goes in some specific space-time region. However, the black hole is not such a thing. So it's like a star, a strange star, but it's also shining. It has a temperature. Okay, that's the starting point of my talk. Now, so I'm going to about the holography. The holography, the key point says there's some black hole, and it wants to claim black hole is some quantum matter. So something like this. So there is a black hole here. This is a star, strange star, and it may be in some secret way is equivalent to some quantum matter. This is called the quark-gluon plasma. I'm going to explain later, or some high temperature superconductivity, something like that. Very strange condensed matter physics. So I want to claim this by holographic principle. Okay, one way, there are many ways, but the one way to visualize that is, so this red one is the black hole, and you can imagine the screen surrounding that black hole. Then you get, again, this is a three-dimensional picture, but you have a two-dimensional world surrounding this red black hole. And there may be some dynamics inside this bulk. And there may be some projection of some dynamics in this bulk to this boundary. And then by studying three-dimensional dynamics and projecting that dynamics into the two-dimensional screen, you can get some physical quantity. And that physical quantity can be some property of the quantum matter here. Okay, that's the mental picture. Okay, and there's a very important question: is which object here corresponds to which object here? That's very essential but very difficult question. So I'm not going to answer that question, but I'm going to assume there is correspondence between these two dynamics. Okay. Now let me modify my mental picture a little bit. This is a spherical object, and I have a spherical the screen. But I want to have a flat space and flat matter. So I imagine there is also black brain, not a black hole. So this is a horizon. The surface, this surface corresponds to the horizon of the cylindric, the spherical black hole. Here you can imagine also there's a black brain, and extra dimension here radial direction corresponds to this x direction. Okay, so there is a black hole, and my quantum matter lives here. Okay, so in Einstein's theory, you can also make this kind of a black brain. Okay, the original one is of course black hole, but you are mathematicians, so you can do everything if you want, right? Good. One more modification. So I said the black hole in the sky has a temperature. If something has a temperature, it radiates, right? Then as time goes on, it will disappear. This is called the black hole evaporation. As time goes on, everything evaporated. However, because I want to study quantum matter, I want to have a stable black hole. If it's evaporating, then it does not correspond to the quantum matter. So then one of the way to do is I put the black hole in the box. So if you put the black hole in the box, then black hole will radiate. But because of the wall of the box, the radiation will come back. So there is a kind of attraction effect. Okay, so I will put that in the box. In a mathematical or theoretical terms, I'm considering the space-time with a cosmological constant. Okay, here, let me explain a little bit more. So this is Einstein. In his original theory, there was no cosmological constant. He liked a simplest thing. I also like a simplest thing. But he introduced cosmological constant because he wanted to have a stationary universe in his days. So then mathematically, there are three choices: positive lambda, zero lambda, or negative lambda. So this is original theory. And now our universe is believed to have a positive cosmological constant. And then probably you have heard about that. Our universe is accelerating. So it's becoming bigger and bigger. However, so that means it's kind of a anti-gravity effect, right? It's a very strange thing, but it can be realized by thinking about the positive cosmological constant. And De Sitter actually devised this theory with Einstein together. And the mathematically another choice is this. So that's anti-De Sitter because it's anti of De Sitter. So anti-De Sitter space means the universe has a negative cosmological constant. It means additional attraction. Okay. So then I'm considering this anti-De Sitter space. The black hole, so that's this meaning. So now I have a black hole. I have extra attraction because of this wall. There's lambda plays that role. So I have a negative lambda, then I have a black hole in a box. I have an attraction effect. That means I have a stable black hole, then I can use this stable black hole to study quantum matter. Okay? That's one way I like anti-De Sitter space. So that means it's clear I'm not talking about the black hole in the sky. So I'm talking about the black hole in the mathematical world. But I feel more comfortable to say this to mathematicians because mathematicians can do anything. But sometimes the physicists don't like this. Okay, so good. Now this is not again now modify the mental picture. So I don't have a black hole. I have a black brain. So this is extended infinitely. Okay, black hole and a black brain. And I have another screen here. Okay, and there is a three-dimensional dynamics in this picture, and the three-dimensional dynamics will be projected to this two-dimensional plane. So this three-dimensional dynamics corresponds to the gravitational dynamics, and this two-dimensional reflection projection corresponds to the quantum physics. Okay, and this means you can imagine there's some rope, and if you just fix this endpoint, then there's an extra attraction to the inside. So this rope will make this shape. Okay. So then you can imagine this. So if you want to study some physics from here to here, your rope will go more inside. If you want to study physics with a short distance, then you don't need to go inside. You can stay at the boundary, near boundary. So that means if we want to study this physics, you have to explore the dynamics more close to the horizon. If you want to study this physics, you don't need to understand horizon physics very much. Okay, and I'm not going to explain that very much, but this is very interesting. There are many very interesting observations here. There is a quantity, the so-called quantum entanglement entropy. I'm not going to explain that, but this is very important quantity. Intuitively, so you can just focus on this line, and you can ask this question. There's some degree of freedom here and some degree of freedom here, and you want to understand the quantum entanglement between here and here. And there is some formula. So you compute something at this boundary. And very interestingly, that formula simply can be computed by computing the length of this loop. So in one side, you just compute the length. In other side, you compute very complicated things here, very different things. But if you compute, they are the same. There must be something here, right? So that's called quantum entanglement entropy. Good. So now let me tell you about a little bit more holography. Why holography? So this is the image of the holography. This is a three-dimensional shape, but this is two-dimensional plane. But the information of this three-dimensional shape is already encoded in two-dimensional plane. But this image can be seen by just using laser and by using interference pattern. But without doing this, already there is information here. Everything is here in two-dimensional plane. Now the question is, this physics or this information is in two-dimensional or three-dimensional? That's the question. And you can choose, actually. It's a matter of convenience. But the whole point is they are equivalent. But here, you can see something, you can say something. But here, you cannot say anything. We call this is difficult question. This is easy question. Okay? So sometimes, if we can reformulate difficult question in a higher dimension, the problem can be simpler. Okay? So this kind of extra-dimensional idea is everywhere in the theoretical physics. It's also very popular in 10-dimensional string theory. I guess someone here also studied something about this, right? And this extra-dimensional theory came out for the first time by Nordstrom. And this is about the electric theory. So originally it has 4 components, but he just added one more component and tried to explain the gravity by using this theory. However, I like this story. People didn't like this. So his work was not very much appreciated in his home university. So when he applied for the travel grant, the comment was, one can study the 4th dimension at home without any trip abroad. Nowadays, it's true. If you just do the research grant application, someone obviously make the similar comments. So, but thanks to Rak-Kyeong, I can come here. I'm talking about this extra dimensional theory. Okay, so there are another persons about the Kaluza-Klein idea, and they also considered generalized gravity to the second rank tensor in 4 dimension to the 5 dimension. Then they wanted to also combine gravity theory and the electromagnetic theory. Okay, simpler version of holography. So suppose you want to study one-dimensional harmonic oscillator problem. So just going up and down. It's a very simple one-dimensional problem. This is one dimension, but this is time direction. But anyway, this is one dimension. However, if you want to study this in a kind of a simpler version, then you can also think about two-dimensional motion. So in two-dimensional motion, you can think about just a uniform circular motion. This is easier. But if you just project this motion to the one dimension, you will find the harmonic motion. So it's your choice. You can study harmonic motion in one dimension, or you can study harmonic motion in 2 dimensions, just a circular motion, and just project. Okay? Someone think this is easier, someone think this is easier, but anyway, equivalent. Another one. So because you are mathematicians, this is too easy. So you want to solve these differential equations, and sometimes you will find it's easier to go to the complex plane. You don't need to go there, but if you go there, the computation is much easier. But the whole point is, after computing everything, you should project. You should come back. That's my point. So now, somehow you find some very difficult problems, physics problems or mathematical problems in some space-time. But you just extend one more direction, extra dimension. And if you can reformulate that easier problem, then I would go there and solve there and just project down. That's the idea of the holography. So to me, this part is easy. I can see. And the gravity is easy for me. The solving Einstein equation is easier. But this quantum physics is very difficult to compute for some reason. Okay, so then I would make a gravitational system instead of directly tackling this problem and solve this and want to project down. Okay, good. Okay, so one example, very historically very important example is the quark-gluon plasma. I'm going to explain what the quark-gluon plasma later. However, the point is, this quantum matter has some physical property which is called a shear viscosity per entropy ratio. Whatever it is, it's computed as a 1/4 pi by using gravitational theory. And then people try to compare this gravitational result with the experimental or computational result in the real world. And it's almost the same number. And there is no theory predicting this number in physics. Only gravitational theory can predict this number. So this is, again, very surprising result. And these two string theory and nuclear physicists said this is the first of useful paper to come out of string theory. So I agree 50%. Okay, so now there's a black hole there. There is a temperature. Then it's equilibrium physics because I already defined temperature. But you want to understand better about some object. You always perturb that and see what happens. You just poke and you just want to see what the reaction is. So then that's a non-equilibrium physics. And you put something and there will be some deformation. And as time goes on, it goes to the equilibrium property. And by observing this process, we can understand the physics, okay? And this is called the transport coefficient, like viscosity or conductivity. And I'm focusing on this linear response regime. Linear response means you poke the system very gently. Then this formula, this is your source. You just poke system, you perturb the system, and your reaction, the reaction of the system is proportional to this perturbation. Okay, so this is proportionality constant. That's the linear response theory. Okay, and so I want to. Okay, now let's talk about the quantum quark-gluon plasma. So this is the proton. Because you are mathematicians, maybe I have to explain a little bit better. This is called U quark and U quark and D quark. There are 3 quarks in the proton. And the proton is composed of the 3 quarks, and plus this yellow one is the gluons. But at a low temperature, they look okay. But if you heat up, you give energy to this proton, then that every component will be separated. Okay, this is a quark, and this red one, yellow one is a gluon. So this is a quark and gluon, but it looks like a plasma. This is a quark-gluon plasma. This is a proton and neutron, hadron things. Okay, as temperature goes up, becomes this. It's very reasonable, right? Then how can we make this system on Earth? Not in the history of the universe, we already had that area. So right after the Big Bang, it's a very hot place. So then we already had a quark-gluon plasma phase. But as time goes on, the cool down, then we see the hadrons. Okay, but on Earth, we also can make the quark-gluon plasma state. For example, in the rig, this is the accelerator and a heavy ion collider in New York. So the gold collider. And here, this is large hadron collider between the France and Swiss. It's a bigger one. This is really big. And the bigger than the gold, you can just collide two lead ions. And to estimate, so we are here. Am I right? We are here. So can you guess if there is a ring, how far it goes? It's a hint is 27 kilometers circumference, 27, this much. So this is the KTX Ulsan station. This is really, really big. Okay. Now the 100-meter down. So this is inside the view. Yeah, so human is here. Yes, it's a very big pipe. Okay, skip that. Good. So that we call that a little bang. Big Bang is a real universe history, but we also can make a quark-gluon plasma state in the accelerator. It's very important because we can understand early stage of the universe on Earth, right? It's very important. So about quark-gluon plasma. So what do we want to understand about the quark-gluon plasma? We want to understand about the shear viscosity of the quark-gluon plasma. Okay, so let's forget about quark-gluon plasma. There is some liquid thing, something here. So you want to understand shear viscosity of the matter. Then shear viscosity means you just push the layer, then how momentum, so easier language, it's the friction between the layers. Right? That's the shear viscosity. Now, if we want to study the quark-gluon plasma, shear viscosity of the quark-gluon plasma, you have to have a quark-gluon plasma here, and you have to push the layer. Of course, it does not make sense, right? Then the people devised a very nice, genius method. So here, there are two heavy ions, and two heavy ions collide. Then we will have the almond-shaped quark-gluon plasma at the beginning. And we want to observe what happens as time goes on. There are two choices. One choice is, it looks like again, almond to the another direction. This is this way elongated, but in this case, this way elongated. Or as time goes on, it can be just spherical. So you can imagine if there is a frictions between layers, then it will be spherical because of the friction. But there is no, if friction is very, very small, then in this case, there is a momentum gradient is big. So this part goes fast. So you will have an elongated shape. So by looking at this shape, people can judge how shear viscosity is big or small. And of course, this is experiment. People can compute or measure something. That value was 1/4 pi. And the gravitational computation. This is basically, think about the black hole, two black hole collision, for example, right? Then we can think about what happens. So, or even one black hole is okay. So this is a linear response theory. So there's one black hole, and you just poke the black hole and see how it goes to equilibrium again. Then the value is almost same as this. So that means in order to study quark-gluon plasma property, we can also study the black hole property. And more interestingly, this is the very cold Fermi gas of the atoms. You can just collect many Fermi the atoms. This is the gas of the Fermi atoms. And by using the trap, the light laser trap, so you can make an almond shape from the beginning. And you just turn off your trap. Then this almond shape becomes elongated like this, very similar. So very different object shows a very similar behavior. So this is the my favorite picture. So here, let's start from here. This is a temperature. This is pressure. And ultra Fermi gas is here. Very low temperature and pressure is low. And quark-gluon plasma is very high temperature and pressure is here. The very high pressure. Then of course, these two objects are very, very different ones. But suppose if you study some specific physical property, if they are the same somehow, you need explanation, right? Very different, but for example, shear viscosity are the same, almost similar. Then it can be just a coincidence, right? Of course, it can be coincidence, but if it's not a coincidence, you need a very good reason. So in this case, we think that reason is a strong correlation. If the constituent of the matter are very, very strongly correlated, then shear viscosity is small. That's the basic idea. So here, this is eta over S, and this is the temperature. And the Coulomb plasma is here, and ultrafilament is here. And there are many other experimental value. And the idea is the black hole in the ADS space is representing the universal property of the quantum system of the strong correlations. Okay, so that's the basic idea. And let's go back to let's go to the ADS CMT. CMT means the condensed matter theory. So about the conductivity. So people say it is the conductivity is the first quantity to measure because it's easy to measure, but very hard to understand. And in the nature, there are matter, which is called strange matter because the property is strange, or non-Fermi liquid. So in order to study some quantum matter, we also can use the Einstein theory. This is gravity theory. Einstein terms and cosmological constant term or Maxwell terms. Okay, so you don't need to understand what it is, but the whole point is this is a theory for the gravitation, theory for the black hole. And the idea is you want to just perturb this theory. Then the perturbation is described by the second order differential equation. Now this part should be easy. Here the function is AX. So I have a second order differential equation. So it is delta AX. And all the other things are just a function of R. Okay? So then I think everybody can solve this. This is a very normal second order differential equation. And then because this is a second order differential equation, you have two freedoms. So at the boundary, at one boundary, for example, for large R regime, you have the initial value and this is called leading value or sub-leading value. You have two free parameter, and all the other things will be determined by this second order differential equation, right? I'm more comfortable to say here to the mathematicians. If I say the physicists, then I have to explain more, but it's okay, right? Two unknown parameters are enough. Now these are two, but this corresponds to source, and this corresponds to expectation value. I cannot explain why, but you can accept that. Then, for example, source means you act something. For example, electric field, you act something, and the result is the current. So this is a current. Then the ratio between current and electric field is conductivity. That's the observable in physics. So ratio between these two. Mathematically, they are unrelated. So then conductivity is not decided, not determined. However, for some reason, they are related, then conductivity is determined. In the mathematical term, what happened is here at the boundary, we have electric field and current. But those boundary values are propagating into the bulk by using this second order differential equation. And just propagating here, and this function will meet horizon. But the black hole horizon has a very special property. It's a singular point. Because of the property, the propagating value should have some relation. And that's one constraint. That constraint determines the relation between these two values. That determines conductivity. Okay? So that's what happened. So in my talk. So this is the most important equation in my talk because I'm going to talk about machine learning about this. Is it clear what I'm doing here? So I need two boundary conditions. you start from here by two boundary conditions. But if you just randomly choose two boundary conditions, something strange happen here. In order to impose a regularity condition here, specific the pair should be chosen, and that relation gives you the conductivity.
Is there any dependence on shear viscosity?
Oh, sorry. No.
Yeah.
Yes. Okay. So, okay, I can talk about this. So, in condensed matter theory, in a normal theory, so the resistivity is basically inverse of the conductivity. Resistivity is proportional to T squared. This is temperature. But some strange metal has a linear dependence. That's why it's strange. In the standard theory, standard metal has T squared, but in the strange metal, it is T linear. And it's very important property. Maybe I can talk about this later by using table. Sorry, let me skip that now. Okay, let me skip that now. Okay, I'm going to skip that. Good. So from the holographic perspective, in order to study some quantum method in this plane screen, you have to use one more dimension. And in this one more dimension, there may be some gravitational dynamics, strange black holes. Then by studying this, after studying that, you project to the boundary and you understand this quantum theory. That's the paradigm of the holography. Okay, finally, let's go to the deep learning. Good. So then it's very interesting to say this extra dimension has a structure of the deep neural network. So we can ask the machine learning question in this holographic in two ways. The first one is just what I said. Can you understand this extra dimension as a deep neural network? Or without using this analogy, can you simply use a deep neural network as a useful tool to study holography? So both questions, I think, have a positive answer. But today, I'm not going to talk about the first question. I'm going to talk about the second one. Good. Now, deep learning as a methodology. So traditional, I think it does not, it's also belong to all science, the mathematical model. So normally what we do is we just build up, we also propose some model, equations, actions, integrals, whatever. We just propose some action, the model explaining nature. And to check if that model is good for the nature's law, then we make a prediction, theoretical prediction. And then try to compare the experimental data, compare with the experimental data. If it works, then this model is accepted. If it does not work, and you change this model, you add some terms or you change some parameters until you get the correct experimental data. That's a very traditional way of science. But the AI way is a little bit different. You just start from the big data, experimental data, and ask a machine to say about the model. And then we have a model generated by machine, then make a prediction and compare that prediction with another experimental data. See if it's working or not. Okay. So this is a novel way, AI method to understand the physics law. So if I compare these two, this way is very traditional, and we always use some intuitions and principles, some symmetries, and I think we need a genius. So nice model always has a name of the model. Those are genius. Without genius, it's very difficult to weigh. However, you need a good machine. You need the money and good machine. Then you don't need a genius. However, I would like to say that knowing this model is not the end of the story. This is the beginning of science. So machine learning is just a helping tool. It cannot replace the human. That's my opinion, and is in my life. Good. So now let's talk about deep learning. So I think this is very standard cartoon. Artificial intelligence includes machine learning, includes deep learning. There are many, many techniques of deep learning. Probably in this workshop, there are many things will be introduced. However, my talk is just a dot. I have to make a little more smaller. Just one way of using machine learning. Okay, so don't appreciate my methodology too much. It's just a very specific way, simple way. So this is Koji Hashimoto because I stole this page from Koji Hashimoto's talk. But I guess you already know this deep neural network, right? So I'm not going to explain that. But the details, if you don't know that, it's okay. The details doesn't matter. So what I want to say is just one here, universal approximation theorem. So any function can be approximated with more hidden units. So by using deep, this is the deep neural network. This is a deep neural network. And I just assign some number here in the circle and assign some number this line. And I have some algebraic rules to give some number. So I have a number here and many numbers and algebraic rules and will give me some number. That's the deep neural network. So that means this guy is basically a function approximator. I have a function approximator. That's clear, right? Good. So then the whole point of the theorem is I can make any function by using this deep neural network. Of course, if you have a very complicated, if you want to make a very complicated function, then you need a more complicated deep neural network. Okay, so this is the kind of existence theorem. Okay, so I think example is the best to explain something. So let me explain simple one. This is the paper I wrote with undergraduate students. The title looks fancy, ADS deep learning made easy, simple examples, but the content is kind of boring. Just the title looks simple. But this is very simple problem, one-dimensional problem, fractional physics. I'm working in the Newtonian theory. So this is F equals ma. My F has two components here, the mg, gravitational part, and some unknown part. This is ma, right? F equals ma. Now, the normal problem is F is given. And then this is a second order differential equation. And if initial conditions are given, then you can easily solve this differential equation, no problem at all. Whatever complicated F, no problem. These days, Mathematica can solve this very easily. Now, the problem is, suppose I don't know F. If you don't know F, then how can you solve this differential equation? You cannot solve. No answer. You cannot solve. Now, the question is different. I want to find out F by using big data, initial big experimental data. So I will do my experiment. I just put some balls in a different position with a different speed, many, many, many times. Then I will measure final speed at some point. Then I have a big data. Then my question is, what is F satisfying all these big data boundary conditions? That's my question. Then, of course, maybe you will think about this. Okay, so probably I will try this. This is traditional way. That means you only need to find A and B. You just assume this, and you compute, and you want to find out A and B, satisfying all that big data. From the beginning, it does not work because there are only two unknown parameters, but I have a big data. So that means my function is very, very complicated. So if it did not work, then you may want to add another one. You may want to add another one, something like that. That's the traditional way of science. If you are lucky, probably you can find the answer. but let's not do that. Just ask machine. And then by using the big data, we can just ask what the f is. In this case, this is the algorithm. I have a big data. I put the data in here in this equation. And then starting f is just random because we don't know the answer, just a random. Then of course, the computed final speed will not the same as the real final speed. Then I will compute the difference. That's called the loss function. If we are very lucky, this loss function can be 0 from the beginning, but it's very improbable, right? So then now this f is approximated by deep neural network. Then the machine will try to change. At first, the machine assign a random number. But in order to reduce this loss function, machine will change these numbers and try to change f. So here, the true one is gray and the starting one is red. This is random f. And after 20 epochs, 20 trials, then it becomes orange. And after 500 trials, the machine found the answer. Okay, this is a very simple example.
Yes.
What is the WN?
So WN is some number assigned this line. Bn is some number assigned this circle. Because I didn't explain the algebraic rules, maybe I can explain that after this talk. But for now, it's not important. Machine have some rules.
Just the weight of the technology.
Yes, the weight and bias.
If WM is determined, could we determine the exact f?
Exact. Yeah, sure. Yes. Right. So now let's generalize. So I started with this example. Then this is the one specific example of this general form. This is second order differential equation, ordinary differential equation. And suppose A, B, C, the all red one is unknown. If you can solve this problem by machine learning, of course, you can solve this by machine learning because the principle is the same. And one of the example of this equation is this. Here, maybe you may remember, this is the example of the whole conductivity equation. This AX is the function, and here R is the variable, and omega is just a parameter, mu is a parameter, everything is fixed. Now, F is unknown. This is my equation. However, I have this boundary condition. At the boundary R equals 0, the leading value and subleading value, two unknown coefficients, the relation of two coefficients are given as experimental data. Then by using this big data, what is F? That's my question. Now, mathematical question is clear? Yeah, so this is an ordinary second order differential equation, but now this coefficient is unknown, but I have boundary data, and I want to find out F satisfying this boundary condition by using machine learning. But I already showed how to solve this. That means I can solve this. Let me generalize this. Now this is coupled equation. But I have more unknown coefficients. But I have to have also two functions, f and g, right, then coupled. And this is the example of this general form. Here, this is looks very complicated, but this is also equation derived in holography theory. Just focus on mathematical structure. I have two functions. This is a second order, and this red circled one is unknown. But again, the same story. I have a boundary value. That's experimental data. And I'm asking what zeta f is, eta is. I can do that if I can do this. Okay. So this is my paper about that story, but I'm not going to explain this. Okay, so let me not explain. Oh, let me go to the easier part. Good. Another example. So I just introduced how to solve second order differential equation by using machine learning. How solve, I mean, I want to find out equation itself. Okay. Here, another example is integral equation. This is electric field. So, okay. Situation is there's a disk here, circular disk. And suppose there is a charge distribution depending on R. And then if charge distribution is given, then you can compute electric field on this vertical axis. Then this is the mathematical formula. So everything is fixed. If sigma R is given, just put it here, then integrate, then you can find that electric field at every point. Okay, so integral part is easy. Now the inverse problem. So I'm doing experiment. I'm measuring electric field on this vertical z-axis. Then my question is, what is charge distribution? Then I can also use the machine learning. So for example, this easy, I just made this just for toy example. Initially, the same story. Here, the gray one, initially machine just assume anything, this randomly. Then, of course, this EG will be different from the experimental value. Then machine trying to reduce the loss function. Loss function means experimental EG and computed EG. So machine try to change the sigma R in order to reproduce the experimental value. Then finally, the machine was able to find this sigma R. So this has something to do with quantum entanglement entropy. So in the holographic theory, because I think I cannot explain in detail, but I think I already say something here. This is a boundary, and there is a length here, and you want to understand the quantum entanglement between this regime and this regime. And of course, we have to compute a very complicated quantum computation here, but forget about that. You just compute the length. Then surprisingly, answers are the same. This is, for physics students, this is really that moment change your life, right? There is a quantum theory that is very different from the gravity or geometry. You just computed something in quantum theory. And then you just compute the length, it's geometry. Somehow they are the same. Then we have to understand something here. Anyway, in the machine learning case, I can give some big data here. Then I can ask, what is this red part in the mathematical language? Now, let's finish by saying the physics. Here, let me go back to, now here, what's the meaning of this F? This F has explain the property of the space-time, property of the black hole. So in my picture, okay, so let's say there is a black hole here, and black hole has some property, and say there is some function Fr, and this is called the in-blackening factor. And for a given Fr, the property of black hole is determined. And this R is this extra dimension. And again, here, this is my world. And you can imagine any Fr here. But the space-time geometry will be, for example, completely determined this Fr. And there may be some dynamics here, but the dynamics will depend on this Fr, background Fr. So everything is fluctuating around this Fr. So what I'm doing is I'm giving some constraint. That constraint is the experimental data, mathematically just a boundary condition. And so by using machine learning, I'm trying to find F. What form of the F will give the experimental data here. So this F is that F. Okay. And of course, this is the simplest case. That's why I have only one F. But more general case, I have more unknown functions. If space-time is more complicated, then probably I have more unknown functions. But the whole point is this kind of coefficients explains the background geometry. That's the solution of Einstein's equations. Okay. Okay, so I have 3 minutes, right? Okay, thank you very much.